11.1 empirical and theoretical probability. So we're putting names to things that you've been doing for a very long time already. Um, so let's put these names and formulas to things we've been doing. So a little bit of history about probability. So probability is used in many areas. I mean, finance, medicine, insurance, elections, manufacturing, educational tests, measurements, genetics, forecasting, investments, opinion polls, science, game of chance. Literally, probability. It is all over because we need to know what are the chances of this happening. And every time you say that to yourself, what are the odds of this happening? You're talking about probability. Well, odds are different. You'll find out the difference between those two things. So here's some just historical names in the Renaissance area of probability, and it's just to show you that they have been studying probability for hundreds and hundreds and hundreds of years. It's nothing new. We've been talking about it for such a long time because it's that natural curiosity to explain why is this happening. Anyways, definitions. An experiment is a controlled operation that yields a set of results. The possible results of an experiment are called its outcomes. An event is a sub-collection of the outcomes in an experiment. Empirical probability is the relative frequency of an occurrence of an event and is determined by actual observations of an experiment. Theoretical probability is determined through a study of possible outcomes that can occur from the given experiment. So they sound exactly the same because mathematically we find them the same way, but in reality they're two different things. So empirical probability is something I can see, like rolling a dice. I can see that. Or tossing a coin. I can see that. Or collecting data from my patients. I can see that. Theoretical probability is, say I ask the classroom, what's your favorite color? And you say green. And then I can say, well, if 4 people out of the 20, so out of 1 out of 5 light green, that means 1 out of 5 in the school light green. So you see how I'm only testing one population to account for everyone? So that's theoretical probability, but they're found the same exact way. So empirical probability is P of E equals event E has occurred over total number of times the experiment has been performed. So you don't have to really memorize the formula because it's kind of common sense. Coin toss. In 100 tosses of a fair coin, 44 landed heads up. Determine the empirical probability of the coin landing heads up. So we want the probability of heads. So that's what H stands for, heads. So it's how many times it happened over the total. So it's how many times it occurred over total tosses. So it occurred 44 times, and we tossed it 100 times. We always simplify. So I know to divide by 4, but you can divide by 2 until you can't anymore. So we can divide each of these by 4. And when we do, we have 11 over 25. So what that means, most of the time, if you were to flip a coin 11 out of 25 times, it would land heads for this experiment. And that's about right. Try it. It's true. Because that's almost half, right? And there's only 2 sides to a coin. See? Puzzle pieces starting to move and piece together. All right, blood pressure reduction. A pharmaceutical company is testing a drug that is supposed to help reduce high blood pressure. This drug is given to 500 people with the following outcomes. Blood pressure reduced 379 people, unchanged 62 people, increased 59 people. If the drug is given to a person, determine the empirical probability that a person's blood pressure is reduced, unchanged, and increased. So our first one is reduced. So for reduced, it was 379. So we want the probability of reduced. So that's 379 of them. total 500 people got the drug. So out of 500 people. We can't simplify there. Just 379 500 have nothing in common. So that's it. That's our answer for A. All right, let's do B together. So for B, we want to know unchanged. So the probability of unchanged. So unchanged was 62 out of total 500 people who got the drug. So both of these are even numbers. That means we can divide by 2. So when we divide by 2, we get the probability of unchanged equals 31 over 250. All right, I want you to pause this video and try C. Do this. Pause it, try it. I hope you did it. Welcome back. Let's do part C. So how many increased? So let's look at increased. It's 59 out of the total people who took the drug, which is 500, and you cannot reduce because 59 is prime. Empirical probability in genetics. So you probably remember this from biology. I know I do. I mean, I literally remember this graph and this chart, this picture with the pure yellow, pure green. I mean, all of it looks the same. It's pretty crazy. It has not changed from my biology book in like sophomore year of high school. I swear to you, it looks the same. It's super weird. Anyways, so Mendel, he's the person who kind of talked about genes and where we are today with them is because of him. So he developed the laws of hereditary by crossbreeding different types of pure pea plants and observing the relative frequencies of the resulting offspring. These laws became the foundation for the study of genetics. You do not need to know any of this, but I wanted to show you how we can use probability in biology. Like, without probability, there is no biology. Like, you have to have that probability because that's how things happen. That's how mutations happen. That's how things happen with your genes and cells. So that's why probability is super important. Anyways, you don't need to memorize any of that. I just want to kind of throw it to another subject for a second and give light on how math goes everywhere. Without math, we have nothing. Are equally likely outcomes. If each outcome of an experiment has the same chance of occurring as any other outcome, they are said to be equally likely. Tossing a coin, that's equally likely because there's only two sides. So half of it is either going to be heads or tails, right? Theoretical probability. It's the same way we calculate probability with empirical. It's no different. So it's number of outcomes favorable over total number of times we're going to test it. So determining theoretical probability. A fair dice is rolled, found the probability of rolling some things. All right, so a dice looks like this. So that's our standard die. For my nerds out there, this is a D6. Okay, we can't. I mean, I could do a D20, but why have to deal with 20 numbers? Anyways, so we're rolling with a 6-sided dice, and this is what our dice, all the faces look like. So we want to know the probability of rolling a 2. So total, there are 6 faces on a dice. There's only 6 outcomes, right? It's either going to be 1, 2, 3, 4, 5, or 6. And only one of them is a 2. So 1 out of 6, you'll get a 2. And that's about right. About 1 out of 6 times you're going to get a 2, maybe a little more, a little less. Because this is probable. It's probability. Probably. All right, B. We want to know the probability of an even number. So we have 1, 2, 3 even numbers. So total we have 3 even numbers out of 6 numbers on a dice, which is 1/2. Isn't that right, though? Half of the die is even? Yeah. Alrighty, part C. We want to know the probability of a number greater than 3. So greater than is that symbol right there. So greater than 3. So greater than 3, we have 4, 5, 6. So that's 3 of the faces of the die are bigger than 3 out of 6. So that's half. half of the die is greater than 3. That's true. Alrighty, part D. So part D is the probability of rolling a 7. That's impossible because a 6-sided dice does not have 7 on it. That doesn't exist. 7 is not on the dice, so it's impossible means 0. 0 means impossible. Alrighty, part E, a number less than 7. So for part E, the probability of a number less than 7. So 1 is less than 7, 2 is less than 7, 3 is less than 7, 4 is less than 7, 5 is less than 7, 6 is less than 7. So that's all of them. That's 6 out of 6 is less than 7, or 1. 1 equals 100%. So that means 100% of the time, if you roll a die, it will be less than 7. No duh, because it's either going to be 1 through 6. Important probability facts. The probability of an event that cannot occur is 0. The probability of an event that must occur is 1. Every probability is a number between 0 and 1, because it's either I can't happen 110% of the time, right? It's only going to happen between 0 or 1 time. So that is, probability is always going to be between 0 and 1. The sum of the probability of all possible outcomes of an experiment is 1. So if you take out all possibilities of an experiment and add them together, it will equal 1. The sum of the probabilities equals 1. So the probability of something happening plus the probability of something of not happening equals 1, or vice versa. So let me show you what that means. So we remember the probability of a 2, that was 1 out of 6, right? So the probability of not a 2 on the rest of the die is 5 out of 6. If you add these up, don't you get 6 out of 6, which is 1? That's all that is saying. You could also use this formula to figure out any other portions. So you can find what's the probability of it not happening, or what's the probability of it happening. We'll talk more about that through the lessons in chapter 11. Alright, a deck of cards. If you don't know a deck of cards, you gotta learn it. A best way to learn a deck of cards, there's a game called Crazy Eights. If you look up online, you can find the game. It really teaches you a deck of cards, and it's fun. It's like the OG Uno. If you've ever played Uno, it's the OG Uno. It's not as fun, of course, but it is the OG Uno. So there are 52 cards in a deck. If you have like little siblings or nieces or nephews, you should play 52 card pickup. Look it up, it's fun. Anyways, so the deck consists of 4 suits. Suits. I always say that every time. I don't know, my entire life, 4 suits. Hearts, clubs, diamonds, and spades. Each suit has 13 cards, including numbered cards, ace, and ace through 10, and 3 picture cards or face cards, jack, queen, and king. So if it's a picture or if it's a face, it's the same thing. Hearts and diamonds are red, clubs and spades are black. There are 12 picture cards, 4 jacks, 4 queens, and 4 kings. So this is what a deck of cards looks like spelled out. You have hearts, diamonds, or clubs, diamonds, spades, black and red. Ace is always a lower card. Don't let anyone tell you it's a high card. They are lying. All right. So select one card from a deck. Determine the probability that the card is an 8. So we want to know the probability of an 8 card. So if we look at our deck of cards, there are 4 8 cards. So there are 4 8 cards out of total 52 cards, which simplifies to 1 over 13, because we can divide by 4. There are always 4 of each card. So then I want to know the probability of not 8. So if I know the probability of an 8, I know the probability of not 8. It's 1 minus 1 over 13. So 13 over 13 minus 1 over 13, that's 12 over 13. Or you could have done 13 minus 1 and you get the 12. So the probability of not 8 is 12 out of 13. All right, the probability of a club. So clubs are these cards right here. We have 13 of them. There are 52 cards in the deck, so 13 are clubs, 52 cards total, which reduces to 1 over 4. Doesn't that make sense, though? Because if there's 4 sets, it's one of the 4 sets of cards that make up the whole deck. Yep. And if you don't see that, that's okay. We just divide by 13 and get 1 out of 4. All right, let's determine the probability of a jack, queen, or king. Picture cards. So there are 4 jacks, there are 4 kings, or queens, and there are 4 kings. So there are 12 that we can pick from. So that's 12 out of 52 cards. And of course, we can simplify. Usually you're going to be able to simplify. So when we simplify, 12 out of 52. Now, if you just... I don't want to make it too difficult. Okay, never mind. Let's just keep going. Let's simplify normally. So we can divide by 4. And when we divide by 4, we get 3 out of 13. But doesn't that make sense? Because there's 3 out of a total 13 in each. Hopefully it's coming together. It's okay if it's not. Just do it the fraction way. All right, E. We need to know the probability of a heart or spade. Or excuse me, heart and spade. That's 2 very different questions. A heart and a spade. Think about that. Can I pull 1 card out of a deck and have it be a heart and a spade? 1 card. Nope. That's none or 0. I'll write down why. So the reason why is that you don't have cards or 1 card that is or are a heart and spade at the same time. So it's none. Alrighty, part F. It wants to know the probability of a card greater than 5 and less than 9. So greater than 5, that's 6, 7, 8, but less than 9. So we have 4 6 cards, 4 7 cards, and 4 8 cards. Isn't this really similar to part D? It is. So we have a total 12 out of 52, which is 3 out of 13.